let me know when we're good to start.
You should be good.
Any announcements? Okay. Are you good to start?
Anything else?
Yeah, any other announcements?
Well, Wednesday week, not this Wednesday, Wednesday after that, my birthday. Still don't know what I'm going to spend. But there may be some kind of. Actually, the traditional thing is to go out on a Tuesday night, wait for it to midnight. And then Wednesday is my day off. I haven't figured it out.
Okay.
Take it away, yes.
So I will note that this talk was written for mathematicians who don't know about type theory, so I might be beating a dead horse a little bit here with the structuralism, given that everyone here does a little bit of type theory. But okay, let's begin. So, suppose you're asked, is 3 in n? Yes, no. This is an interactive talk, please, please. Yes, yay, okay. Okay, we're all happy that 3 is in fact a natural number. Okay, okay. So the answer to this is yes. It's fine. No, quotes, because... Okay, so a little trickier is this question. Is 0 in n? Yes.
Yeah.
Right, so for the purposes of this talk, we will take 0 to be a natural number, because algebraist, not an analyst. So as long as the meaning of this statement is clear, this has a meaningful and unambiguous answer. Yes. Right. How about this one? No, right, okay. So this you'd answer no, right? Now, suppose you were then asked, is pi in log? Right? We might take a second again before answering no, but no for a different reason than before. Pi is a number and log is a function, so this doesn't make sense. So it's not no because it isn't an element, it's no because this doesn't make sense. So this illustrates the intuitive notion of type, that objects are equipped with the kinds of operations that they are compatible with. You can't divide a bool by a string. And sometimes, along similar lines, we see mathematical statements that are kind of grammatically incorrect, so to speak. For instance, these statements. Do we agree that these are kind of not fully correct statements, right? Is 0, 1 closed? Well, in what ambient space or in what topology? Is Z a group under what operation? And so on. Or for slightly less subtle examples, is a rectangle prime? Does a prime converge? So the notion of a type formalizes this kind of grammatical errors. We all intuitively use types throughout mathematics, beyond this all. Yes?
Is reaction subjective?
Yes, it is. It is. Okay, no, it depends on what the ambient set is, but.
I mean, I'm thinking it's just like it's both projection and projection can be projections, right?
Yes.
No, like no.
Okay, as an element of the natural numbers, as we will define it, it is not subjective. Okay. But so this is the kind of ETCS also has its own encoding problems, is what I'm pointing out here. Okay, so we use types in other ways in mathematics. For instance, what does this mean? Well, it depends on what the type of object A and B are. If they're ints, matrix, tuple, whatever, they do this. So the point is that in mathematics, we like to use types. But in the standard foundational framework of ZFC that's used in a lot of mathematics, outside of algebra, Rickerman, don't at me, then in ZFC, everything is a set. Moreover, membership is a global relation defined on sets. Any two sets can be compared for memberships. So this implies that is pi and log is a well-formed question that has a yes or no answer. It's a proposition. Because of this, the way ZFC uses the word set is quite different from how we'd like to think about sets. In ZFC, pi is a set, so is log, but if you ask any working mathematician to try and list some of their elements, you're unlikely to get a meaningful answer. So the benefit of this is simplicity. Everything is a set, so we can have a unified set of rules to deal with everything in a simple way. And also, everyone kind of learns how to manipulate sets from school onwards, right? So it's relatively easy to teach. On the other hand, we lose this basic notion of type, because everything is of type set. As demonstrated by is pi and log, this isn't always a sensible thing. For instance, take the axiom of regularity. Here's another axiom of ZFC. It says every non-empty set X has an element that is disjoint from itself. But if you take X to be any ordinary set, say the real numbers, what does an element of this look like? Is this empty or not? It is in fact empty. But the problem is we have an operation being applied to two things which doesn't really make sense to apply it to. 3 is, as we think of it, doesn't make sense to apply intersections. So the one response to this problem is to say that ZFC includes a set of standard encodings of mathematical objects. As we discovered yesterday, or not a few days ago, as Rickman spent 3 hours trying to explain to me that sets are not products, or products are primitive in sets, which they're not. So we can compare this situation with computers, right? So all these constructions encode down to pure sets, in the same way that in a hard drive, all these different types of files encode to binary strings, ones and zeros. In the same way as if you try to read an image file as a text file, you get a bunch of nonsense. If you try to do operations on sets in ways that are not intended to be used with, you also get nonsense. That doesn't mean that the files you're encoding are useless. In the same way, ZFC is not useless because it lets us do this. It's just don't do this in practice, right? And of course, ZFC is a very good foundation. It works on a technical level for a lot of mathematics. So in analysis, for example, you don't really care about the foundations that much. And I think this is a very reasonable thing. But is there a more mathematically pleasing way of avoiding this kind of thing other than just ignoring it, right? So one enlightening exercise, as posed by Benacerraf, is to consider the question, is 3 in 17? So Benacerraf describes two children, called Johnny and Ernie, who have learnt about natural numbers from axiomatic foundations, as opposed to the commonly preferred method of counting, which he calls the vulgar way, philosophers. However, when we're learning from foundations, there is no choice in the matter. So Johnny is taught that there is a set, n, of natural numbers, that what ordinary people call natural numbers. There is a specified natural number called 0, and there is a function called the success function that is defined like this from n to n. Right. The normal properties of natural numbers can then be derived as theorems. For instance, the vulgar way of counting is just the pure axiomatic idea of cardinality. Addition is definable through simple recursion, and so on. Having constructed everything in his first order theory, it's clear that Johnny can now communicate with the vulgar. With all common extra mathematical uses of numbers like this being encoded as sets. Right. Note that all we have done is specify these three things, and everything is derivable from there. So this information is both sufficient and necessary to characterize the natural numbers for communicating with the vulgar. Now, this story could have also been, yes?
You need some sort of least.
Huh?
You need some sort of smallness thing.
Getting onto that. Okay, so this story could have also been told about Ernie, the other child that Benacerraf describes. Like Johnny, Ernie is provided with a set of naturals, a specified element 0, and a successor function. So the two are equally knowledgeable about the natural numbers. And in conversations with ordinary people, they're in complete agreement. We know how to add, we know how to count, and so on. However, the problems first arise when they ask, is 3 in 17? So Johnny argues that this statement is true, while Ernie disagrees. But they try to reconcile this, they talk to ordinary people and ask what they think, and they think it's complete nonsense because obviously these are numbers. So if we look at the information they were given, the source of this discrepancy is obvious, right? Johnny's success function is defined like this. So 3 is in 17. This is the von Neumann construction. whilst Ernie's is defined like this. The source of the disagreements is obvious, but how to reconcile them is not quite as clear. But this isn't the only disagreement between the two systems. So, proposition: a set X has n elements if and only if there is a bijection between X and a natural number n. It's true for Johnny and not true for Ernie. So their notions of cardinality also disagree in this sense. Right. So this is clearly the source of the problem, but how do we fix this? It's not obvious how should be, how the two accounts should be reconciled with each other. Each account in isolation is equally valid and correct, but neither one is to be preferred over the other. Each one is perfectly valid as models of semi-rings of natural numbers, right? So if we accept Johnny's model as good, as we commonly do, there's no good reason why we shouldn't also accept Ernie's. But then we run into this problem. Of course, we could accept both and accept that this is a true statement, but this is clearly absurd. Let's not do this. The alternative is that at least one of these accounts is wrong, right? So the belief that there is a true account is called set theoretic Platonism. Is that there is a true account, there is some correct assignment of natural numbers 0 and s. But Spinozarov rejects this as ridiculous, saying basically that if we're saying that 3 is a set, then there should be a good reason why it is that, and not just by fiat, it is this set. But on the other hand, all of these accounts seem to be the same. They agree on everything we actually care about for natural numbers. Again, when we're talking to the vulgar, everything's fine. It's only when we actually look at these set relations that are the problem. For the purposes of describing the natural numbers, and natural numbers only, any of these accounts will do, because they only differ in aspects that aren't inherent to natural numbers. And this is the idea behind structuralism. So mathematics, as we actually use it, doesn't demand of the natural numbers that they actually exist as some concrete, specific set, only that they have some kind of structure on it. When we work with them, we only require that they support simple recursion, that they have a semi-ring structure, and so on. And in fact, this is usually how we describe most objects in mathematics. So a vector is anything which satisfies the vector space axioms, and a tensor is anything which satisfies the tensor axioms. Neither of these definitions actually describe what a vector or a tensor is. They only describe how they behave. So to a structuralist, mathematics is this kind of study of structures independent of what they're composed of. As seen by this kind of definition, this is how we usually do things in maths. So it's kind of strange that one of the most popular foundations of mathematics does not follow this approach. ZFC is distinctly not structural, as we've just seen. But it doesn't have to be this way. Structuralism tells us that it's meaningless to ask whether this equality holds or not, because it's not asked in the context of the rest of the natural numbers. For instance, we know 3 is not equal to 2 because 3 follows 2, 2 is strictly less than 3, which is a property of the natural numbers. But it seems wrong to argue that 3 should or shouldn't be the set, because 3 has 1 element, or 3 elements, or 17 elements, because this isn't a property of natural numbers. We don't know this, right? The number of elements of 3 is not part of its structure. So what makes the number 3 is precisely its relations to other natural numbers. And because the number 3 does not have any set relations, we argue that it's not a set. To find out what it is then, structuralism says that the correct question is not what is 3, but what are all the natural numbers? Or more precisely, what structure are the natural numbers? So in ZFC and other traditional material set theories, the basic primitive notions are of sets, elements, and memberships. So most of the questionable statements we've encountered have come predominantly from the fact that membership is a global relation on sets. It's just too strong, right? Whereas in practice, we usually only compare sets that are already contained in some ambient parent sets, or in some surrounding context, in other words. So for instance, let's define a function in material set theory. So informally, a function is a special kind of correspondence between input objects and output objects, where one input goes to exactly one output. It's a functional relation, is how we're going to define it. So materially, we can define a function as a relation where we capture the pairs. Note that this construction requires ordered pairs and products, but we can define those. And given the relation, we can tell if it's a function if it satisfies this property. The next step is a trick that we commonly use in mathematics. We drop the distinction between the informal notion of a function and its representation as a set, and we say that this defines a function. For now, we'll note that this works on a technical level, and a lot of analysis, non-higher algebra can be developed for this, but there are some conceptual hurdles for this definition. For instance, you can't recover the codomain of the set, of a function, and again, not a problem in a lot of cases, but you can patch this to fix this. But in algebra or topology, this can cause problems, right? Another problem is, if you look at these functions, the identity on A and the inclusion of A into B, they're the same set, because they're the same mapping. But we usually don't think of these functions as the same thing. Like one of these is an identity map, and the other one's kind of shoving A into B, right? We don't like to think these are the same. And this isn't just a conceptual problem. If, for instance, A is, say, the circle and B is the complex plane, then these two maps induce different first homology homomorphisms, right? So in topology, this matters. Oh, yeah, so we can see how functions are derived from these primitive notions and how the kind of problems that this causes. But the way we're going to be doing it is we're going to be looking at how sets relate to each other. And because functions are precisely these relations, we're going to be taking these as primitive. So structural set theories axiomatize sets and functions. Moreover, functions are inherently attached to a pair of sets, so we have a lot more locality in our theory. And another side effect of this is that all of our constructions will be isomorphism invariant. All of this means that our theory will be well-lended to be described by category theory. So we're gonna revise everyone's favorite lemma, as it's the extensionality axiom for structural sets, basically. All right. So let one be a set with all elements. For any set X, a function's 1 to X picks out points. And also this is how we'll define elements in arbitrary categories. So we take maps from the terminal into your object, and these are elements. And we can use maps from other things to capture other features. For instance, paths, sequences, and topological loops. More generally, we call these maps generalized elements of shape S, right? So a global element is of shape 1, and these are our points, right? So now in material set theory, sets by the extensionality axiom are characterized precisely by their elements. To what extent are structural sets characterized by generalized elements? So for instance, if X is a topological space, these maps yield these different information about it, and we can get more and more information by looking at these maps. We get the points back, we get the connecting components, get pi1, and so on. By looking at more and more maps, we get more and more information, but how much information can we cover? The Oneida lemma says all of it, right? And that is what we're going to be using. So this is the Oneida lemma, don't care about this. We care about this probably. Right, this is the nice probably that we care about. Actually, we also care about the other direction, but not written that. So while sets are characterized by elements, structural sets or arbitrary objects are characterized by generalized elements. Yes?
This is the covariant unit.
Yes.
You were talking about the conjugate unit on the before.
It's fine. They're all isomorphic. Yes.
So you don't need generalized elements. Like you'll already go if we want.
Okay, that depends on one being a separator for your category, right?
Okay, but like that's the property of the category of sets, right?
Shh, you're spoiling the talk.
I mean,
We will talk about this later. Yes, this is the property that will axiomatize. Yes. Oh, sorry. How do I see this?
Repeat the question if possible, is what Jan asked.
Oh, the question was, doesn't this already hold if, aren't two objects already isomorphic if you look at the maps from 1? Yes, because 1 has a special property in the category of sets, which we'll talk about later. Okay, are there any other questions? I can't see them here. Okay, good. Okay, cool. First thing to abstract, how do we characterize subsets, right? Because let's take these 3 subsets, these 3 sets. So in a material subset, let me say that again. In a material set theory, these first 2 are subsets, and the third one is not, right? But they're all isomorphic as sets, because there are bijections between them, which means that the subset relation does not respect isomorphism. Categories don't care about how we label elements. What we care about is how they embed into X or not. So I'm going to use this arrow for monomorphisms. So given a bunch of monos into X, we can define a preorder on them like this. So if we have A into X, B into X, then we say F is less than or equal to G if F factors through G, right? Note that this factorization is unique if it exists because G is mono and will equalize anything which makes this commute. So we can also go the other way. G is less than or equal to F if it factors the other way, and if we have both, then they're isomorphic morphisms. So in other words, we're looking at the mono subcategory of the slice category over X. So with this, a subobject is an isomorphism class of monos into X, right? And given a mono, A into X, we write this for the subobject represented by X, or sometimes we write A with a slight obese notation. But to see how this works, let's go back to the previous example. Right, so these three sets are isomorphic, but let's look at how they inject into X. So if we take the map which sends all of the elements to 1, these all factor through each other, right? Because if we send 2 to cat, then 2 goes to cat back to 1, so these factor through each other, and these are all isomorphic morphisms. Therefore, they represent the same subset, namely the one that picks out 1, right? On the other hand, even though we have the same domain here, if they go to different elements, then they don't factor through each other. They don't agree in their images, so they don't witness the same subset. So the top one is the subset containing the singleton 1, and the second one is the subset containing, the first one is the subset containing the singleton 2, and the second one is the subset containing the singleton 1. This is what really distinguishes the two in the context of being a subset of X. They don't factor through each other. And this also helps to resolve some questions in material set theory. True or false? False? Oh, okay, naughty. Right. So let's, oh, don't want to do that. Oh, okay. Right, so the integers are equivalence classes of naturals, and the reals are these things. Pick your favorite encoding. But the point is, it's clear that the integers are not actually a set of the natural numbers, of the real numbers. But when we actually interpret this in the non-set theoretic way, this is clearly not a good thing to have. So this kind of solves it. The question is not about the elements. This is not the right question. The question is there a function from Z to R that witnesses this subset containment, right? And yes, there is a mono that picks out the integers from R. So yeah, structural fixes this. We can also put partial ordering on subsets of a fixed set X. So we write this if they factor through if any representing mono factors through each other. And this notion is rather suggestive that this is the subset relation, as the actual subset relation on subsets. But note that there is a subscript X here. This subset relation is local to a containing set X, unlike the material version of this. Now, what about memberships? So an element, so remember when you say X is an X, we mean a map from 1 to X. This is a member of a subset, and we write this version, these are not the same thing, this is subset X, if it factors through, right, as a diagram like this, right? So this is what it means to be an element of X, is that it's a global element, and this is a mono, oh, that should have a mono tail, excuse me. So it goes through that, and we say that X is an element of this subset if it factors through it, right? And again, it's local, so we don't have this question of asking whether two arbitrary sets are members of each other or not, right? So there is another way of describing subsets, right? So we can characterize them as a function from X into 2, where 2 is the 2-point set, basically by using indicator functions, right? It's true if it's in the subset and false otherwise. And this process is a bijection. We can go the other way. We can go back to the subset by taking the preimage of true. Now, recall that preimages are a special case of pullback. So the bijection says that this is a pullback. There's a unique function here to here, such that this is a pullback. And nothing in this diagram is specific to sets, so you can actually abstract this in general to any arbitrary category that admits pullbacks. So a subobject classifier is any object, omega, and a map true from 1 to omega such that for every mono here, there is a unique morphism here that makes this a pullback. Right. And this is the direct abstraction of the indicator function characterization of subsets. We can give another characterization. So given a object X, we write sub X for the class of subobjects of X, called the subobject poset of X. If the category has finite limits and is locally small, then every function from X to Y induces a map of subobject posets in reverse order by pullback, right? So remember, monos are stable under pullback. So if we have a map here into X, sorry, a map here into Y, then if we take pullback along F, then we get a map into X. In other words, every function here sends subobjects from here back into X. So this defines a contravariant functor from C into set, and the subobject classifier is precisely a representation of this functor. So in other words, there exists an object omega such that this isomorphism is natural in X. And this kind of corresponds to the idea that as we said earlier, that a subset is a map from X into 2, is into the truth values, right? Cool. So subobject posets also allow us to abstract other constructions about subsets. So given two monos, given two subsets, A and B, we can construct that union and intersection as the product and coproduct inside of the poset, interpreted as a category. Note again, these are local to X. This is a common theme, everything's local. And for some intuition why this is true, kind of the intersection is the maximal subobject that factors through both of them, which is the same thing as a thing equipped with maps to both of the domains, which is just a product, and same with the other direction. So we can construct intersections and unions like this, but local to subsets. So we've talked about making smaller sets. How about bigger sets? First, let's look at products. So given two sets X and Y, that product, what is it? What's the element of a product? Well, it's an element of X, an element of Y. So in terms of maps, it's this, or in terms of Hom sets, it's this. So this is the property we want, but Ioannidis tells us that we shouldn't look at global elements, we should look at all elements. So we really want this isomorphism, right? Luckily, if we take the product of sets to be the categorical product, this is precisely the universal property. So we get this for free. But there is a slight ambiguity once we move past binary products. So these two objects kind of implement the same interface. They're all ordered triples of stuff, so they should be isomorphic. In other words, our theory really doesn't want us to be able to distinguish these at all. So isomorphism works for these. That hides the distinction between them. But what about if we have more objects? So the problem here is mirror isomorphism isn't enough in this case because, well, there are multiple ways of rebracketing these equations, right? So if we take the first one, if we move from the first expression to the second, there's two ways of doing that, right? We could rebracket the inner one, so move this bracket into Y and Z, and then the outer one. Or we can move the outer one and then the inner bracket, right? There's two paths to go from the first one to the second expression. And even if all of these are isomorphic, there's no condition that says that these two paths are equal. So this means that if we didn't have any other conditions, our theory would be able to distinguish these two objects. You just transport a morphism along one of the paths and along the other, and then check that they're not equal. Yes?
This is basically why we say unique up to unique isomorphism instead of saying unique up to isomorphism.
Yes. Yeah. Okay. You can do it that way, but also So the point is that you don't want to be able to distinguish these. Isomorphism is enough. You need unique isomorphism or coherent isomorphism, and the structure which we're going to be using for that is monoidal structure on the category. So this is the definition of a monoidal category. Yes.
But if you already specified by your first property, you probably need to there are all like the isomorphisms are all unique because they all have subsets in the first property.
Yes, they are.
Okay.
I mean, I slightly reordered the slides. This is supposed to go last.
Okay.
Yeah, okay, this is true. You don't need a monoidal structure. You can use the Cartesian structure on there, and that's fine. Okay. I mean, yeah. What's the timing like? Okay, that's fine. So this is the definition of a monoidal category. It's basically just a generalization of a normal monoid to multiple objects. So for instance, the associator says the thing that we wanted before is that all the ways of rebracketing an expression are equal. And the identity says that if you multiply by the terminal object, or we'll pick it to be terminal objects, but if you multiply by a unit, then it does nothing. Oh god. Sorry, my slides are not working out. Okay, so, oh, there we go. So in set, we have this obvious isomorphism where we send A, comma, B in another bracket C into, we just re-bracket them, and this is the associator that we can use. And this means that set is not a strict monoidal category, despite Rickerman spending 3 hours trying to tell me that it is on Friday. If anyone saw that Zulip post, that's what that was about. And these sets are not equal, but we can take an isomorphism, which means it's good enough for ETCS. And because, in this case, the tensor is given by the categorical product, it's called a Cartesian monoidal category. And the Cartesian, the structure on set has another special property in that it's commutative. And we call this a Cartesian symmetric category. Sorry, Cartesian symmetric monoidal, or symmetric Cartesian, some words. Yeah, so you can swap the order of the products, the product ends, and it's still the same. Okay. An interesting thing, set is also monoidal if you use co-products. It's another structure on it. But the point is that you can use the monoidal structure to suppress brackets and units and everything we're doing. Right. Okay. So the next thing that set supports is internal harms. So in other words, we're trying to abstract function sets. So given an object A and another object B, we can write this for the set of functions between them. The problem is that this is a definition rooted in set membership. We're describing the set by what it contains. It contains all these functions. So we need to characterize this by using only other functions, right? So let's look at functions into this set. Does anyone think about what we're doing here? Yeah, it's currying, right? So this is the same as just applying the first argument and the second argument. So we can define an internal Tom object as something which satisfies currying, right? If they exist for all the objects, then the category is called monoidal closed, or Cartesian closed if this is actual product. Yeah, if you generalize it to monoidal, then you need naturality in B as well. That's fine. Oh. More slides. Okay. I don't have this slide. Okay. So set is locally small because it has all functions between objects. So it's Cartesian closed because all the Helm sets are already objects in there. Right. So in the Cartesian closed category, we use this notation instead of this, and we call it an exponential object instead. So if we write out the defining isomorphism again, this is someone asking a question. Is that what's going on? Why is that popping up? No. Okay. This notation is compatible with categorical products in that these are all isomorphic objects, why we define 2 and 3 to be these. So exercise, try doing this without Unida. It's kind of interesting. But yeah, we can write out the defining isomorphism again, and we can instantiate x as 1, in which case, oh, what am I doing? Sorry. Okay, some more notation. If we move it along to the left, we call it a flat map, and if we move it to the right, it's called the sharp map. Don't need this, that's fine. Okay. So yeah, let's look at this and instantiate x as 1. So 1 times a simplifies to just a times b. So this is saying that the global elements of this object are the same as the maps a to b. So this correctly does what we want. It's the things in here are labels for functions a to b. Do you have a question? Okay. Cool. Right, let's go to the definition that we're all waiting for. So the original notion of a topos was introduced by our favorite algebraic geometer, Grothendieck, as a generalization of sheaves of sets. Every topological space induces a topos, and conversely, a topos, as described by Grothendieck, behaves kind of like a generalized topological space. Oops. Okay, so Lever then, what's my mouse gone? Then generalized this notion further to what's called an elementary topos, which is defined as follows. So it's a category which is finitely complete, so we have all limits. It's Cartesian closed, so we can talk about products and exponential objects. And as a subobject classifier, so we can talk about subsets. So already we can see this behaves quite a bit like set. And this definition seems quite short for something we claim to be so important, but the subobject classifier in particular gives us a lot of structure. So for instance, every monomorphism in the topos is regular. Every topos is balanced, means that every mono and epi, every morphism that's mono and epi at the same time is an isomorphism. And every topos is finitely co-complete, even though it only started with limits. We have more co-limits. And another interesting one is topoi have an epi mono factorization system. Right. So every morphism factors essentially uniquely into the composition of a epi and a mono, and the thing in the middle is called its image. So the prototypical example, as we'll see, is set, but it has a couple of other special properties which it doesn't share with other topoi, so we will talk about that soon. Oh, where's my slides? Okay, so let's talk about some distinguishing characteristics of set, appealing only to obvious properties of sets and functions. First of all, set is not the trivial category. The trivial category is technically a topos. Let's avoid that. And we say this by, one way of expressing this is by saying there exists an initial and terminal object and they're not equal. They're not isomorphic, rather. That's the first property. The second property, I already forgot who asked this. Thank you, Asbro. Yes, okay. The second property is that one has a special, has a thing that can detect when morphisms are equal. Basically, if two functions agree on all global elements of one, then they're equal morphisms. To interpret this, what this is saying is if x is an element, if this is saying if f of x equals g of x for every x, then f equals g. This is just fun x, right? And in particular, it's fun x where we take elements from one. And this property is saying that. We say that one is a separator, right, in this case, because it separates morphisms. So a topos which satisfies these two is called well-pointed. And the next property that we're going to use is natural numbers.
Why the term well-pointed?
Huh?
Why the terminology well-pointed?
Just for the Zoom, could you repeat any questions? Because unfortunately I can't get.
Oh, sure. The question is, why is this called well-pointed? Answer, I don't know.
Thank you.
Has two.
Oh, yeah.
But I don't know why you need it to be non-trivial for that to be true. Yeah. Okay. I mean, pointed. You can get points. I don't know why it's well pointed. Yeah.
I mean, as well pointed doesn't mean anything. The question comes in nonsense.
I mean, well, it means this. It means this. I'm sure if you look on AnLab, there will be some horrible explanation of why it's called this. Yeah, it has points.
It has more than 1 point.
Sure. I mean, if you don't have the separator, it still has points, right? It's just like.
One is also topos, but doesn't have.
Yeah, okay. Yeah. Well, it's pointed. Well, it's pointed. There you go.
Apparently, Fred online says that sometimes the first point is it's not included in the definition of well-pointed.
Okay, fine. That makes more sense then.
Thank you.
Well, why would you have an alias for something which is one sentence anyway? Why would you?
Let's E be a well-pointed topos.
Let E have separator.
Let E have a.
Let E be a topos with a separator, with its terminal object being a separator. That's more fun.
Terminal separator, well pointed, same thing.
I think at some point you're gonna leave off the definitions.
Yeah.
I don't know, like make
Let X be a blip-flop category.
Yeah.
Just make up words.
I mean, one is also a generator.
What? Okay, one is okay.
There is, of course, there are two issues at work here. One of which is chronic offensive vocabulary,
Yes.
and the other is abuse of the hyphen.
The object is a well. You can always send stuff into it.
Yes. Okay. Well, let's just go with well, it's pointed. Therefore. Okay. Right. Okay. So these are some nice properties that we want our topos to have, right? These are obvious things about set. Set is not trivial, and we have well, it's pointed. Okay. The next special thing is the thing we alluded to at the beginning is we have recursion, right? So given, go, stay with me. Right, so given an element and a function x to x, we can generate an infinite sequence that satisfies this, these relations, right? Now, a sequence, as mentioned earlier, is just a function from the naturals into x. So this is really a statement about the natural numbers, right? So writing f for this function, the previous equations just say that this diagram meets, right?
That problem is primitive.
Huh?
That problem is primitive.
Yes, well, we're defining on this. So the natural numbers object is this triple. It's the thing we said at the beginning, right? It's an object, it's a specified element, and it's a successor map. And it has to be universal with respect to this diagram, right? So, I mean, the ZFC also postulates the existence of natural numbers, or at least an infinite set, as a separate axiom, right? So this is our equivalent of that. So the sequence f given, so this is a sequence, right? Because it's from natural numbers into x. So this is a sequence. We say that f is defined by simple recursion of base case x and step case r. So we can define arithmetic operations on natural numbers by using that exponential transposition, currying. So for instance, addition can be defined using the point-wise successor map and the identity, the transpose of the identity, currying identity. What's it saying that on the left triangle is basically saying adding 0 is the identity map, right? And here, adding the successor is the same as point-wise adding the successor. So you can define all your arithmetic operations through this. So the third property that we have is that set has a natural numbers object. Right. The last property of set that is perhaps optional if you're more constructive is that every surjective function has a section. In other words, the axiom of choice. You can also phrase as epimorphism split, right? They have sections. So here are our 4 properties of sets that we like. So we can say sets and set functions form a well-pointed topos with natural numbers object and choice. You may omit this according to your flavor of constructivism. So the category of sets, of course, has more properties than this. For instance, all power objects exist, but that follows from being a topos and having other stuff. The topos is Boolean, you only have 2 objects in that, and so in the subobject classifier. But all of this follows from these properties. The question is then, what conditions do you need to enforce on sets? What axioms do we need to ensure that they form this structure? Well, one answer is ZFC. ZFC sets, in fact, if you look at the category of ZFC sets, it does have a structure. And this is the answer that a lot of mathematicians have in the back of their mind. But they don't often like to think about this answer, right? Because the axioms of ZFC seem, at least to me, slightly removed from how we really use sets in mathematics, right? The specific axioms seem kind of unimportant compared to the end goal of having this structure. And this is the idea of Levert, is to take this sentence as our axioms, right?
Sorry, can you imply there's only one thing that will satisfy this?
Up to equivalence.
What's equivalence?
Categorical equivalence.
Okay,
Meta theory, this actually characterizes the category of sets up to adjoint equivalence. Adjoint equivalence. So you can write that out the adjunction explicitly. Yes.
Is part of the definition of being a topos being locus?
No.
Can you repeat the question?
Okay, the question here was, the question here was, does this imply that there is only one category which satisfies this? Answer, no, there are many, but they're all equivalent, up to categorical equivalence. The question here was, sorry, can you say it again?
locally small.
Okay, does the definition of a topos require locally small? No.
Well, I guess also does the definition of topos require like I'm used to that topos is like a locally presented.
Okay, sure.
Like that sort of smuggles in.
Yeah, no, I get what you're saying. Yeah, yeah.
Yeah.
I mean, I will address this in a slightly later session.
Okay.
Okay, but good question. Yeah, it doesn't require local smallness. Yes, Gil.
So why do you focus on the natural numbers? more general like closure property?
Okay, the question was why do we focus on the natural numbers? It's the simplest kind of thing that supports recursion, I think is basically the answer. It's because I mean it's the same thing with ZFC. You can postulate the existence of large things, but this is kind of the simplest and minimal thing for recursion, right?
But it feels like then you're going to define the more general objects by encoding them using the natural numbers.
Yes.
But you were trying to avoid encoding.
I'm not trying to avoid encodings. I'm okay. The problem isn't to avoid encodings. The problem is to avoid encodings which have bad collisions with existing primitives, right?
I think it's also worth noting that you don't characterize it strictly by like doing something very like you characterize that to a universal property.
That's a good question.
No.
Thank you.
But I think like maybe that's also
Yeah, I see what you're saying. I don't know how to repeat that to the Zoom call because it wasn't a question, it was a statement. Yes, this characterizes things up using universal property, I guess, right? It's not a concrete construction. Yeah. Okay, so as noted, you might think that there is some circularity here. The fact that the topos kind of a category, the definition of a category relies on collections, which kind of feel a bit like sets. But even though ETCS, we've described it using a language of category theory.
Well, also you have harm sets.
Huh?
Also, you were talking about the circularity, the other circularity. I mean, I think it's not necessarily that much of a problem because you're just saying that forms, a tempos or whatever. But like you already have to have a notion of sets, assuming we're doing normal category theory.
You need a notion of collection, which is okay. Let me put this. This is what the next slide is on. Okay, so okay. Even though this is phrased using category theory, this does not need category theory to be phrased, right? We can do this. This is equivalent to the previous sentence. Category theory is just a compact way of writing these axioms. When you write it like this is kind of the comparison to ZFC is hopefully more clear, right? ZFC is not circular because all it says is there are some things called sets, there is a relation between them called membership, and some axioms hold. ETCS says there are things called sets. For every pair of sets, there are things called functions, and there's a partial operation on them called composition, and some axioms hold. Right? They're both first-order theories. So if you throw away the category theory characterization of it and just use this, no problem, right? Is everyone happy with that? They're both first-order theories.
How do you find 0, 1?
What do you mean?
Well, subset set.
Oh, this.
0.
They're defined from 2 and 3.
Yeah,
But that is you empty and
this is one coproduct one. I've just written it like this for.
the union of set,
Sorry, say again.
I guess. The union of set.
The subobject post that thing we talked about. Sorry, did you mean external union?
I mean, yeah.
Okay. That is not in this talk because the construction is complicated.
Okay.
I can show you it later if you come around. Yeah.
I thought you use
Yeah, I mean, you can say this is the subobject classifier. Yeah. You can show that. Yeah, you can show that omega is equal to 1 coproduct 1. Or alternatively, you can construct it, but yeah.
Oh, like you said that finite limits in domain 1.
Finite colimits.
Exactly.
Yeah, it's because I mean, the point is you can construct this object, but this property won't hold unless you have a subobject classifier, right? Yeah, this object exists, but subobject classifier says this correspondence, right? Okay. Does anyone look at that slide longer? Is that good? Okay. So ETCS and ZFC both deal with sets, but these notions are so distinct that calling them both sets is not really helpful. So we'll call a set in the style of ZFC a material set, and a set in the style of ETCS a structural set. So let's have an overview comparison of them. So in ZFC, axiom of extensionality says that two sets are equal if they have the same elements. In ECCS, a weaker extensionality principle is given by the neonatal lemma. Structural sets are characterized not up to equality, but up to isomorphism by their generalized elements. However, we usually, some other question, no. Okay, sorry, I saw something on the corner of my eye. But usually we only care about equality of subsets in some containing ambient sets. In which case, well-pointedness gives us true equality of subsets, right? Because subsets are morphisms, well-pointedness lets us talk about actual equality, not just isomorphism. Whereas material sets, everything's up to equality. And this is perhaps closer to how we like to use sets in mathematics. So another one here, okay, this one is perhaps slightly odd. So elements are always sets in C because everything is always a set. But in ECCS, an element is never a set because it's always a map. Now, this causes some slight clumsiness with encodings that we'll talk about later, such as the subobject classifier, the maps into them are sub-objects, even though they're not actually subsets, so it's a bit funky that way. So another thing that we have is, apart from elements, is natural numbers. So in ZFC, we define the natural numbers to be a specific set. It's what happens if we take the closure of a thing under a successor operation. But this yields additional unwanted structure like 3 being in 17 or not. In ETCS, a natural numbers object is a structural set equipped with some structure such as the distinguished element and the successor morphism. And arithmetic relations are defined in terms of these and these things only. So the elements of the natural numbers in a structural set only have arithmetic relations and no additional properties beyond them. More generally, every single construction in structural sets is like this. An element of a set X is a function into X and has no internal identity apart from being an element of X and is distinct from other elements of X. So this kind of thing basically says that all of our sets are abstract structures that don't have any other side encoding problems. Sorry. So for material sets X and Y, sorry, A and X, we can ask whether A is an element of X because membership is a global relation. This statement is a proposition in the formal sense, meaning that it has a proof value, you can prove it, and it can be combined with logical connectives, quantifiers, and so on. So we'll call this propositional membership. In contrast, if X is a structural set, then this is true if A is a map into X. A is always an element of X. It can never not be an element of X because it's a map into X. So given structural sets, there are things which are intrinsically elements of them. This is not a statement as you would ever prove about two existing things, A and X. If something is an element of X, it is given as an element of X and cannot be anything else. Consequently, this is not that membership is not a statement is not a proposition in structural set theory. So how do you all read this out loud in your head or out loud?
Rule X and all X, but
Right. So you said for all X in R, X squared is greater than or equal to 0. If R is a material set, then formally, for all things X, if X is a real number, then X squared is greater than or equal to 0. Right? We're quantifying over the universe for everything, every and all things. If it is a real number, then blah, 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 and so on.
for all X, open set on the right X.
Yes, right? Okay, this is the thing. When you translate this kind of thing into material set theories, this is hiding an implication. And I've seen many fourth-year students mess this up at work. The point is that when you translate it, you're already doing this. Yeah, that's what you're saying, right? For all X, X and R, blah, blah, and so on. However, if R is a structural set, then this is not a proposition, so this doesn't make sense. Yes?
I mean, if you're doing the first order logic encoding of EGCS, then it would be for all X if cod X equals R. So.
I mean, sure, yes. I'm gonna cheat a little bit.
Okay.
Okay, that is okay, fine. Strictly speaking, if you were doing it, that is how you encode it. But the point is that you don't have an implication anymore, right?
It still is an implication.
So, okay, what was the statement you said?
Like if you're doing the first order encoding of EGCS,
Yeah.
then this is, you have two sorts, objects and morphisms, or if you're really doing it the way the American did it, you only have one sort of morphism.
Yeah.
And then R is the identity
Yeah. Okay. Okay.
on R, and then you have cod, which are sort of morphism to morphism. And then this would be for all X if cod
of X is
equals
okay,
R,
then okay, fine.
then
Okay, the way I was doing it is you allow quantification over restricted. You can quantify over morphisms given the fixed.
well, then it's multi-hyperphysics.
Yeah.
That's the point.
Well, you know,
Yeah, yeah. Do I need to repeat? Okay, for context, the question was, if you do first order encoding, don't you still have an implication because this is for all X, X being a morphism, X, the codomain of X being R, blah, 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 so on. Yes, but you can cheat and allow quantification over.
Point of foundations is you're not going to cheat.
Okay.
Well, one of the things is that you can like choose your actual meta theory in such a way that things become that.
Yeah, I say cheat. I mean,
Right,
you can just
if
define the
you're
meta theory
arguing
to be
for
like
the
that,
meta
yeah.
theory of GCS, then it's not true in GCS, so you're arguing for a different thing.
Yeah. The point is we read it like this, and at least, even if it's not strictly accurate, this is closer to how it behaves in structural sets, right? Because the point is, at least here, X is actually bound to R. You can't have a free-floating element in structural sets.
This is like for all functions to R.
Yes. For all functions that R, this property holds. And arguably, this is kind of right. This is how you read it. This is how we like to use quantification. So this is nicer. So this membership isn't really the same thing as here. This is a proposition that's saying if X is in R, then blah, blah, blah. Here we're saying for all functions into R, and so on. So this is more of a type declaration. So, for instance, this is included in the interpretation of this sentence in material sets, because this quantifies globally. You have weird statements like this, right? Okay. However, we sometimes do want to talk about actual equality of sets, right? So, for instance, if L is a set of complex numbers such that the real part of Z is a half, then a lot of people are very interested in this statement, right? Okay. But note that we have two memberships here. We want to talk about propositional membership here. In ECCS, this is handled by the fact that we have an ambient set, right? L is a subset of C, so what we're saying is, for all functions 1 to C, we're quantifying over functions here. If blah, 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 then does Z factor through L? This is what this is saying. So we have a type declaration membership here, and we have a propositional membership here.
You can just rewrite this to subset of C, right? That's what it is.
We know L is a subset of C.
Oh, yeah.
That's what we're using for this.
And the property with a particular property, you're right.
Yes, that's what allows us to use this. So we can talk about propositional membership if we have a containing ambient set, in this case, C. So we're declaring the type of Z is this function, and we're asking, does it factor through this subset, this morphism? So ECCS allows us to talk about equality of, propositional membership, as long as we have a containing context. Also, all of this discussion also follows for subsets, the subset relation, same thing. You can talk about propositional if you have a containing set. Okay. So this is what we have. We have propositional membership only, which means you have to quantify over a bunch of stuff. And we have type declaration, but we can use propositional patterns in context. Hold on, let me check what I've got on my next slide. Okay. I'll skip this one. Fine. Because I'm doing this in MSP, let's have a quick comparison to our favorite foundation. So we can kind of compare the situation, and structural sets behave a bit like homotopy types, except they're all zero truncated. So the goal of all of these foundations is to kind of give us objects, and we want to identify them in certain ways. So in material sets, we identify sets up to strict equality of elements, whereas structural sets identify them by isomorphism and coherences, by observable behavior, maps in and out of sets. Homotopy types identify objects by all levels of observable behavior. So while structural sets collapses everything above first level, homotopy types, well, we keep all that information. All the identifications are made explicit by being kept as higher identities. And from this perspective, kind of the coherence of the Cartesian structure on structural sets is kind of the extensionality of material set theories, right? And of identity types and homotopy type theory. So in all three cases, the point is to rule out being able to distinguish sets in a way that are observationally the same, right? The difference between the three approaches is how aggressively we do this. So material sets erases these distinctions by strict equality. Structural sets does this by isomorphism, and homotopy type does it by equivalence, where we record all of the identifications. Okay. Let me just go back a slide. Nope. I didn't need to do that. Okay. So we do have some issues with encoding as well. So I mentioned at the beginning that we have some kind of weird things in ZFC, like 3 being an element of 17 or not. Oh, I'm slightly over time. Okay, I'll make it quick. ETCS also has kind of weird problems where we have this isomorphism, but elements of this aren't literally functions A to B. They're only labels for functions A to B. To actually extract the functions that they're referencing, we need to apply an evaluation map, and so on. So ETCS also has this kind of problem where material sets are actually better in some cases. So function sets, power sets, it's actually helpful if those sub-objects actually are sets and not functions, but ETCS can't have that. The solution to this is type theory, is what the point of this is. Was that your point? Okay, I think I'll leave it there because I'm slightly over time. Yes, question?
No.
You were just stretching like this?
Something like that, but I think like.
Okay. All right, thank you for coming. Any final questions?
So, there are saying that like material set theory, like a function is a special kind of relation.
Yes.
Why are we so interested in the category of sets and functions, not the category of sets with relation?
You should ask Mike Shulman about that.
Can you repeat the question?
Okay.
Products does not have the universal property. The categories.
So the question was, why are we focusing on this category of sets and functions and not sets and relations? I can't find a slide. I'll leave it.
It's better as a double category.
Yeah, so there isn't a similar axiomatization to this called SEER, sets, elements, and relations, which attempts to do that. It axiomatizes rel rather than set. As for why we're doing sets rather than rel, it has a nice characterization as the top was. SEER is quite a bit more involved in my opinion. And rel doesn't, yeah, as you said, it doesn't have universal property for products. I think unions are nicer in rel though.
Well, the union district.
No, just actual unions, right?
Unions of relations.
Unions of sets.
Unions of sets.
The characterization of them is, huh?
Like what do you mean? Disjoint unions of sets? Unions of subsets of a larger set? What?
Unions of relations.
No, of actual sets. Okay, the objects.
Axiomatic.
Okay, but that's usually disjoint ones, right?
I mean, you can.
Union doesn't have meaningless.
No, but you can construct index unions in ECCS of like actual sets,
Whatever.
like objects in the topmost with blah blah and so
But
on.
that's not. But union is never isomorphism here. It's a meaningless.
Well, they're important for like other things, right?
No, but like how do you define them in us? You define them if you're only if your definition, if your constructions are all up to isomorphism, then you cannot construct anything that is
Oh, God.
constructible up to isomorphism.
I think you mean unions of subsets.
No, I mean unions of actual sets. This.
Yeah, no, those are unions of subsets.
They're in there. Yeah. Omega.
Yeah.
Okay, sorry, yes.
Yeah, with
Yeah.
respect to X. Yeah.
Oh yeah, I forgot about the X there, yes.
We have a question from Fred. What about things like large cardinal axioms? Are they natural to formulate structurally?
So ETCS is actually slightly weaker than ZFC. I think ETCS is missing certain coproducts. I think the example that Leinster gives is if you look at natural numbers, coproduct, power set of natural numbers, coproduct, and so on, you're missing all of those. So you can bring it up to the strength of ZFC by adding in those coproducts. For large cardinals, I haven't looked into that as much, but I believe you can formulate. I did see like a singular paper on this. I can't recall it right now, but you can add large cardinal assumptions into this, I believe. But I don't think anyone's worked on that. I don't think people really work on ETS in general.
Well, you can talk about if the relevant thing with ETCS is like strategic universes.
Yeah.
So you can postulate like in various inaccessible universes.
Yeah. I mean, yeah, you can encode both of the universes in this relatively simply, but okay. Is everyone enjoying the stratified background?
We all enjoy those books electrocuting each
Dave, one comment, which is that in your last comparison, you said so material set theory has global membership, but set theory has global identity types. We're just pushing the problems on this.
You're pushing the problem infinitely far into a stack of infinity groupoids.
Okay.
It's not reassuring to be reminded that we all work with
Yes. Oh my god, it's the associator. All right, we are over time.
Thank you.
I just want to know, is it category that with this opportunity?
Yeah.
Oh yeah, it is.
No, I mean, it's not.
No, but I can make products tomorrow. Yeah, I tried to understand all these things. Yeah, we can go shit, right?
You can define products very formally as subset relation, but that's
There's just the.
so right. The problem is that
No, but I want to know what the topic
opening up
the problem is that
a